Hello and welcome to this webinar on construction stages. My name is Isaac and I work with customer relations and technical sales at Strusoft. With me, I have also Attila, which is the responsible developer for the construction stage feature in FEM-Design. He will be available to answer any of your questions during and after the presentation. So please provide your questions in the GoToWebinar interface. Since we are so many attendees, I won't be able to answer your questions on the live stream, but we will keep the webinar active after the presentation is done to be able to answer any remaining questions. The agenda for this presentation. I will start out by talking about the background of the calculation and explain the theory and method of the analysis. I will also show some issues and calculation artifacts that you can encounter when using the feature. After this, I will demonstrate step by step how to use the feature inside the program, how to define the different stages, apply the loads, and view the results. Last, I will show some examples and tips and tricks. The construction stage feature is an analysis which will take into consideration the different steps of the building sequence. The sequence can influence deformations, load distribution, stability, and so on. For example, a bridge may experience the largest forces during or just after the construction sequence is finished, or a high-rise building where the deformation during the construction must be taken into consideration to obtain a correct load distribution, or an existing structure that maybe needs reinforcement. For example, in the bottom of the view, we have a slab with an existing deformation, and then we want to add a column in the deformed shape of the slab to reinforce the structure. So these are some examples when the construction stage analysis can be useful. I will continue to talk about the theory that's implemented in the program. The calculation is performed for every defined step with the corresponding loads for that specific step. It is important to note that the calculation is not time dependent. You don't define, for example, how many weeks it takes to build a specific stage. It will only take into consideration the applied loads in the specific stage with time-independent material properties. Here we have an example. So the structure is divided into 3 construction stages. The dead load is applied for every step in the sequence. So in construction stage number 1, the dead load from the elements in stage 1 is applied, and when you go to construction stage number 2, the dead load for these elements are added. So when you run the analysis, the calculation will be performed for construction stage 1, the result is obtained and saved. Then the analysis is performed for stage 2, the result is saved, and then for stage 3, and so on. The result from each calculation is saved and superimposed to obtain the results for the whole sequence. This means that the analysis is linear. There are 2 main methods implemented in the program. The first one is called the incremental tracking method. Here, each stage is built in a non-deformed shape. In other words, each step uses the original geometry of the structure for the objects in the specific stage. This means that the program will reset the deformation between each analysis. After this, the result is added together. Here you can see the result from stage number 1. Then the non-deformed shape of the structure for stage 2 is analyzed with the applied loads from stage 2, and the result from this is obtained, and so on. Last, the result from each step is added together. It's important to note that no elements are elongated in the analysis. Everything has its own original non-deformed shape in the beginning of each new step. However, the result will be very similar to this elongated effect. So this method is typically used for in situ concrete, or where there is an absolute story height created by shimming each story or casting the structure to a fixed specified height. The second method is called the ghost structure method. Here, all objects included in the analysis is modeled in every construction stage. However, the stiffness of the object that's not included in the active and previous stages is set to a very low value. When the object is introduced, it will be activated with its original stiffness. So in our example, we will apply the load from stage 1 and obtain a deformation at the top of the structure, since these elements are included in the analysis but inactive with a low stiffness. The deformation at the top of the structure will accumulate since we won't reset the deformation between every stage. In other words, the objects are activated in the deformed state. This is typically used for precast elements, where the element has a fixed length or height, or when an element is placed in a displaced position. I will continue to talk about different calculation artifacts that can arise. So the implemented method can produce some strange results in certain situations. This is called calculation artifacts. The most common artifact when using the incremental tracking method is this kind of behavior where we obtain a jump in the deformed shape. In this specific situation, the structure is loaded with a vertical load. But since the stiffness between the walls to the left and the columns to the right are not the same, it will result in an uneven deformation. Since the next stage is built with the perfect shape without any deformation, the summation of the results will be a bit strange in the interface between the different stages and also in the total global deformation shape. This may also appear when applying a horizontal load in a construction stage calculation using the incremental tracking method. Another artifact that can appear for the ghost structure method is a load transfer in an element which is not added yet. This is because the element is included in the analysis but with a highly reduced stiffness, as I explained previously. However, since the stiffness of an element cannot be zero, there can be an unfavorable stiffness relation between an inactive element and the active elements. In this example, we will add the blue column in a later stage using the ghost structure method. In this case, there is an unfavorable stiffness relation between the bending stiffness of the existing beam and column compared to the reduced axial stiffness of the added blue column. In our example, this will produce a small axial load in column number 1, even though the blue column is not added yet. But this is because the reduced stiffness is still fairly high compared to the bending stiffness of the other elements in the system. This issue will arise since the stiffness of an element can't be zero. The reduced stiffness is obtained by dividing the original stiffness value by 10 to the power of 5. This will, in most cases, produce a very low stiffness, but if the element has a very high starting value, it can still have some residual stiffness left. This is important to note when using ghost structure method and adding different supports in later stages, since the support has a very high stiffness to begin with. I will now demonstrate the feature inside of FEM-Design, and the workflow looks like this. I will start out by defining the construction stage in the Structure tab. Then I will continue to define the loads that will act during the construction stage in the Loads tab. I will then choose the method in the calculation window, so either the incremental tracking method or the ghost structure method. So I will swap over to FEM-Design and our example structure here. This is a 4-story building. It is a steel frame. Every connection is rigid, and I have defined 4 different stories in the model. Every profile has the same section type and material, and all connections are rigid. I will start out by defining the construction stage by going to the Structure tab and opening the Construction Stage tool over here. This will open up this window. Here I am able to manually define different stages, or I can generate the stages by the stories that I have defined in the model. I will use this Generate by Stories button to generate 4 different construction stages according to my 4 defined stories. I have also an option to set initial stress state. This feature will exclude all deformations from this construction stage, but save stresses and internal forces. It is mainly developed for the soil where you want to obtain stresses in the soil material, but not have any initial deformation from the soil stage. So in our example, I will leave these blank, but otherwise I would check this button here. I also have some settings here, how to handle newly created elements or moved or modify elements. So I can check this checkbox to automatically assign newly created elements to the story that it's connected to, or move auto-assigned elements when I move elements between stories. So in my example, I won't make any changes to the geometry, so it won't really matter, but I will keep it as the default values here. I can press OK, and I will end up in this view. Here I can scroll between the different stages that the program has automatically generated. I can always go back and change the different stages by clicking this button and add more stages or rename them or make any other changes. I can also reassign different objects to another stage by using the pen and the reassign to list here. So let's say that I will reassign this bottom column to stage number 4 instead. So I will choose story number 4 and right-click on the column. Now, when I scroll through my defined construction stage, I will see that this column is added to stage number 4 instead. I will change this back and include this in story number 1. So this is how the construction stage will look. I can also illustrate the construction stage by the color schema by opening up the color schema function, choosing beam, column, and truss, and choosing the construction stages. Here, the different elements will be colorized depending on the construction stage that they're assigned to. I will click Apply and view my structure. I can also select the construction stage ID on different elements to show it in the graphical view. I go into the settings menu, and in this case, I will select bar elements since it's only a structure of bars, and select the construction stage ID checkbox and click OK. Here I can see what construction stage the different elements or objects is assigned to. I will turn off this option just for now and continue working with the model. When I have defined the construction stage in the Structure tab, I will move on to the Loads tab to define the different loads and how they act during the construction stage. So I have defined one load combination called test, and this includes a line load on every level, like this. I will open up the construction stage tool in the Loads tab over here, and here I can select how the different loads will act on the story. So first I have the number of the construction stage, the name of the stage, and also if I have selected any initial stress state. This is of course selected in the Structure tab as I previously explained. Then I can activate a specific load case, give it a factor, and select a partitioning. I can also see in the tree structure here how the load is applied depending on my partitioning. I will show the partitioning settings a bit more in detail in the PowerPoint presentation, but there are 4 different options here. So let's move over to the PowerPoint again and talk about the partitioning. So this is the final stage, and I can see that I have applied one line load on every level. Q1, Q2, Q3, and Q4. This load case is called Q in this example. So here I use the partitioning called only in this stage, and I have applied it in the second stage, so it's construction stage number 2. In this case, the program will apply Q1 and Q2 in construction stage number 2, but no other loads in future construction stage or previous construction stages. So in this case, it won't include the whole load Q4, 3, 2, and 1, only 1 and 2. And this is because I selected it to apply on story number 2, as you can see here. So this is only in this stage, partitioning option. The next option is called from this stage on. Excuse me. Here, the load case is activated in the specified construction stage and acts in this and also in the remaining stages. The parts of the load that acts on the previous stories are also activated in the specified stage. So for example, here I will activate the load in story number 2 and choose partitioning from this stage on. This means that in stage number 2, I will apply Q1 and Q2. Then when I continue to stage number 3, I will apply Q3. And then on number 4, I will apply Q4. So in this situation, every line load on every level is included in the construction stage phase. The next partitioning option is called shifted from first stage. This is typically used when you have a flooring load that will act one step behind the construction stage. For example, that you will finish the flooring, which will add a load on a stage one step behind all the way up when I build the structure. So for example, in this case, I will apply the load Q1 shifted from first stage in story number 2. Here, when I go into construction stage number 2, the load from level 1 will be applied. So it's shifted 1 backwards. And when I go to number 3, number 2 is applied. And the rest of the loads will be applied in the last construction stage. So here I've applied both number 3 and number 4. So this is called shifted from first stage. The last partitioning option is called only stage activated elements. So in this case, I have selected only stage activated elements for story number 2. And in this case, I will only activate the load that is assigned to the objects in this specific stage. So in this case, it's only the line load Q2 because it's applied on the beam that's part of construction stage number 2. So this option, which is called only stage activated elements, with this option, the load case can occur in more than one stage. And it can be very useful, for example, if you have a composite structure and you have to handle the dead load in a specific way. So I will move on to the program again. And in our example, I will activate the test load case with a factor of 1 and use the partitioning called from this stage on. So story number 1, the load associated with story number 1 will be applied. When I go to story number 2 or construction stage number 2, the load associated with this stage will be applied, and so on. I will press OK. A good tip is to use the assign load to structure option to ensure that the load is connected to the correct element and to ensure that the load is in the correct construction stage. So in this case, I will use assign load to structure and select the load and select this beam. This is especially useful and important if you use the stage activated element partitioning option, because it can be quite not obvious which part or which element the load is assigned to or acts on. So I will make it like this. Okay, so when I have applied a load in this window, the construction stage window, there will appear some new load cases in this list. Here I can see the final construction stage. This includes all the loads applied in the previous window. I can see the loads and the results from story number 2, 1, 2, 3, and 4. So in this example, I will have the first construction stage without the first load combination without any construction stage. So this is just 1.2 multiplied with the test load case. And then I will have with construction stage. Since the whole test load is applied in the construction stage, I can just take 1.2 times final construction stage. So inside final construction stage, I will find all the loads applied here with the different factors. So in this case, it's the whole test load case with a factor of 1. So if I look at the two different load combinations, it is exactly the same amount of load in this number 1 and also in number 2, because test is part of final construction stage. The whole test load case is part of the final construction stage. In this window, I can also check the stability in a specific stage by creating a load combination. For example, stability for construction stage number 2, and set a factor. And here I can choose construction stage 2, story 2. And I can run a stability analysis with regard to this load combination to check the stability of the structure in this specific construction stage. But I will just keep it one load combination without construction stage and one with construction stage, but it's the same load applied. I will continue and go to the Analysis tab, open up the Calculation window, and go to the construction stages. Here I select the method that I want to use. So either incremental tracking method or ghost structure method. So I will run construction stages and also the load combinations. So if I go into the setup by load combinations here, because I have assigned a load case that is part of the construction stages, the final construction stage load case, this will be checked. This will force the analysis to be linear. I cannot run a non-linear calculation here. And this is of course because I need to be able to superimpose the result from the different construction stages. So I will run the analysis. So here we can see the analysis run for stage number 1. The result is saved, and then the stage number 2 is run. The result is saved. Stage number 3 is run, and the result is saved. And last, stage number 4. And then the results from each stage is superimposed to obtain my load combination called with construction stage. So if we take a look at the results, I have a new result called construction stages, and I can check, for example, the translational displacement, and I can step through the construction stage sequence like this. It is the same for all different results here. So I will really quick open up a new window here so we can compare the two different results. On the left window, I will open up the results for the displacement for the load combination without construction stage. Well, first we can check the reactions just to make sure that it's the same load. And also the reactions here, but this time with construction stage. So let's see the reaction here. We have 96, and over here it's also 96. So it's exactly the same load. The only difference is how the load finds its way down to the supports. So this left without any construction stage, let's look at the deformation. So I will show the deformation without construction stage, and the deformation at the bottom will be 2.3 2.4, yeah. And if I go into this and look at the displacement with construction stage and set a value, I can see that this is much larger. And this is because there is more load in the middle column here. In this left view, without construction stage, this whole section of the structure will deform the same amount because it's the same load on every level. So this will just be deformed the same on every level. So there is basically no normal force going through this middle column. But here, if I take into consideration the construction stages and use the incremental tracking method where I reset the deformation between each stage, I will get more load in the middle column and thus larger deformation here. We can also take a look at the internal forces, for example, the moments. So here it's with construction stage. I will make it a bit bigger. And here without construction stage. You can see that on the left view, when I don't consider the construction stage, it basically looks like a beam on two supports fixed in every end. So there is no load going in this middle column. But here it looks more like a beam supported by three supports. So there is more load going in this column. Okay, so this was a quick demonstration on how to use the construction stage feature in FEM-Design. Now I'm going to show some more realistic examples. So I will start out with a bridge like this. So here I have a bridge defined by bar elements, and I have defined a construction stage that looks like this. So we start by building here and we move outwards like this. And I will close this. You can also see that I have colorized every part so that you can see which part is on a different construction stage. The load supplied is just the dead load in the construction stages, and it's from this stage on. So every new stage that is modeled, the dead load for this stage is added in the calculation. And then I have the load combinations. So the first load combination here, I have 1.35 times the dead load without any construction stage. It's just the dead load, and 1.5 times the live load. But here, number 3, it's the same load combination, but this time I use the dead load calculation from the construction stage analysis. So I use 1.35 times final construction stage and 1.5 times the live load. So if I run the calculation, in this example, I'm using the ghost structure method. I will arrange my windows. I can take a look at the moment distribution. So let's see the top view. Let's say that this is without any construction stage, like this. And the bottom view should be the same results, same load, but with regard to the construction stage. So it's this. So here you can see that the top view, when you disregard the construction stage, this will yield a larger field moment. But when you take into consideration the construction stage, the moment in the field will be very small, since the load is carried to the supports when you take into consideration the construction stage. So this will yield a much larger moment over this support, for example. Let's take a look. It's yeah, and compared to this. So this is an example of a practical example. We can also take a look at the deformations. So this is without construction stage. We have a deformation like this. and with construction stage. So it's larger in this case then. So this was the first example, a bridge structure. I will continue to show a high-rise building like this. So here I have steel columns at the end of this, at the facade, and I have a concrete core in the middle. And the concrete plate is fixed to the core, so it's cast in situ. And then I have defined the construction stages from the stories, and so it looks like this. And here I have applied a dead load on every story, like this. It's the only load in the model. And it's applied with the partitioning option from this stage on. Then I have two different load combinations as before. One without construction stage, it's only the dead load, and one with construction stage. And it's 1 times the final construction stage. And inside the final construction stage, I have the dead load with a factor of 1. So yet again, it's the same amount of load applied. So let's take a look at the results. In this example, I'm using the incremental tracking method. So a common issue is when you look at the internal forces of the bars without the construction stage, you can obtain this kind of behavior where you have compression, negative here, but you get tension in the above steel columns here. And this is because the stiffness of the axial stiffness of all these steel columns are lower compared to the stiffness of the concrete cantilever from the core out here. So instead of the slab resting on the columns, it's the columns pulling the slab down. This is quite common for if you don't consider this construction stage function. So you can also see it if you look at the displacement. You can see that it's not resting on this column. This column is almost pulling the slab down instead. And this is because the relationship of the stiffness between the column length and the slab cantilever. So instead, I want to check the results with regard to this construction stage. So in this situation, I have compression in all my columns, since I will reset the deformation between each step using the incremental tracking method. So this is usually more realistic behavior like this. And if you look at the displacement with regard to the construction stage, you can often see this kind of behavior where you have the largest deformations in the middle of the structure and not at the top. So this is also quite common, that behavior, real life behavior. Okay, so the last example I want to show is a composite structure. So here I have 2 stories, and the composite structure is cast on place. So first it's steel beams, then I will add a concrete plate on top of the beams. But since the concrete hasn't hardened when it's being cast, I can model this using a construction stage. So in this case, I have created the first step. I have only the steel columns and beams, and I have a cover which will distribute the self-weight of the concrete on top when it's being cast. So in this stage, it's only the steel beams that is carrying the load. Next step, I will add a concrete. So this is the step where the concrete hardens, and I will connect the concrete to the beams using a line connection like this. So this is the second step. I will add the line connection from the beam up to the slab, and then I continue to the next level, do the same thing. First cover, then I cast, and it hardens, and I get this kind of structure. So in this situation, it's useful to use the partitioning that I talked about before, only stage activated elements. So the loads that it's applied, I have a dead load, which is automatically generated by the software. Then I have this concrete dead load, which I apply on the covers. So this is carried by the steel beams. And then I have a flooring load when I finish the floor, and then a live load also. So in the construction stage, I will apply on the first step, when it's only a cover and steel beams, I will apply the concrete dead load, only stage activated elements, and the dead load, only stage activated elements. And then I will continue. When the concrete has hardened, I will add the flooring load from this stage on. So in this situation, it's very useful to have this only stage activated element partitioning option. So let's take a look at the results. We can see the construction stage here. So first we have a deflection of the steel beams and columns with regard to wet concrete. So it's being cast on top here. Then I go to the next step. The concrete has hardened. I will add this and apply the flooring load. Then I build the next sequence and hardening. So this is a good way of modeling this kind of composite structure and take into consideration this hardening of the concrete in a construction stage sequence. Okay, I will end now with some tips and tricks and some frequently asked questions. So it's important to know that the rigidity is accumulated in the calculation. So it's not possible to reduce the rigidity of an element. So it's not possible at the moment to remove an object, for example, or to reduce the stiffness of an object in a later construction stage. You can only add stiffness to the model. So, but this can be used, for example, here. Let's say that we have a structure which should be a hinged connection in the first step, but then in the second step, it will be fixed. I can actually apply two different supports here. One support that is only a hinge, and yeah, it's a rotation stiffness in out and in of the plane. But these are set to 0. So it's a hinged connection. And then I apply another point support with the rotational lock like this. So I will separate this into two different construction stages. So the first one is a hinged connection. Then I add this one, and it will become a rigid connection in the second step. So this is possible because I can add stiffness to the model, but it's not possible to go the other way around. So to have a rigid connection first and then go to a hinged connection. But I guess this situation is more common, where you go from a hinge to a rigid connection. This can also be used using, for example, point connection and line connection tools. It's actually part of the bridge here, if you take a look at this. So here, at the end of the construction stage, I will add the last element and two different point connections here. CS9, which is part of the construction stage 9 here. So let's take a look at these. They are a hinged connection. So this last element will be hinged during construction stage number 9. And then when I go to this construction stage number 10, I will add another point connection. In this case, it is a point connection with only rotational stiffness. So here I go from a hinged connection to a rigid connection between two different construction stage 9 and 10, like this. So this is another little trick that you can use, but remember that rigidity can only be accumulated with the current algorithm. Other frequently asked questions is that all shrinkage effects will be handled in the stage where the load associated with shrinkage load is applied. So there is no time dependency at the moment in the calculation. This also applies to the creep value. So the full creep value defined for the concrete material is used in the calculation independent of the construction stage. So no time dependency. So we can take a look at the creep defined. You have this option. You can set creep for SLS and ULS. And this is the one that's going to be used depending on if you're SLS or ULS load combination in the construction stage sequence. So there is no time dependency at the moment with regard to either creep or shrinkage. So lastly, this feature will be further developed and will include more features in the future. So if you have any specific requests, please feel free to contact us and we will take this into consideration for future development. Okay, this concludes the webinar. The session will be opened for another 50 minutes or so to answer any remaining questions in the chat. So please feel free to write your questions in the question area in the GoToWebinar interface, and we will do our best to answer all of them. Okay, thank you so much for watching this webinar. Please keep an eye out for upcoming events on our homepage. Okay, thank you and goodbye.